was a research fellow in the development of an integrated simulator for V2X protocols and applications. And now he is scientist one in Agency of Science, Technology and Research, Singapore. Sir has three major achievements. One in 13 to 15 Anna Senatory Research Fellowship Award funded by Anna University, Chennai. 15 to 16 EMA2 Swagat Fellowship funded by European Commission. 2015, he has business fluke competition and he holds fourth position there. Sir's research interest is model order reduction, model predictive control, non-linear control system, neural network and fuzzy logic, process control, transducers and recording system, artificial intelligence, machine learning, autonomous vehicles, V2X. Sir has 8 publications, international journals, 23 international conferences, and 3 national conferences, 3 book chapters. And today, Sir will be talking about platoon management with cooperative adaptive cruise control strategies of autonomous vehicles. So what is this platoon? Platoon means a method of connecting vehicles either physically or using computer technology so they can travel close together in a group as a way of saving space, fuel, or money. The capacity of vehicles to communicate wirelessly provides an opportunity for innovations in the transport sector. Platooning of vehicles is one of the widely studied topics in the research community. Vehicle platooning aims to increase the capacity of roads, improve traffic safety, and reduce fuel consumption. This work introduces vehicle dynamics on modeling, control aspects, and observes the behavior with vehicle-to-vehicle communication. Most of the work on platooning investigates the control of vehicles in pairs based on the concept of look-ahead platooning. This work emphasizes the design of proportional integral derivative, in short form PID controllers, and model predictive control MPC based on a combination of constant distance and constant headway time policies to operate a heavy-duty vehicle. In addition to basic cooperative adaptive cruise control, the controller is tested and verified, carrying out splitting and merging maneuvers. So with this, a brief introduction to the topic is over to you. You can take over the.
Okay, thank you for the introduction. I'm audible, right?
Audible. You can continue.
Okay. So thank you, Shobhana, for the introduction and in fact what expertise I'm having and describing all those sorts in the abstracts. For today's presentation, I'll be dealing with the topic on adaptive cruise control strategies of autonomous vehicles. So about me, I hail from Kochi, Kerala, and lives in Singapore for the past 3 years. I've done my bachelor's in applied electronics and instrumentation from Mahatma Gandhi University, Kerala, and completed my master's degree in 2011 in electrical drives and embedded control from Anna University. I've passed my PhD in electrical engineering faculty from Madras Institute of Technology campus, Anna University, in 2017. A part of my research was done at University of Pardubai's Czech Republic through Erasmus Mundus exchange program. So that is a Swagata Fellowship. So there I carried out my research and came to Anna University back to defend my thesis in 2017. So my thesis title was on reduced order modeling and control for typical industrial process. So the typical industrial process includes like a binary distillation column, the petroleum industry, multi-component distillation column. And I also tested my algorithms on various other processes like GUNT 010, which is a speed control, and GUNT 101, which is a level control system. Also done some model adaptive controllers, model-based adaptive controllers in conical tanks, spherical tanks, 4-tank systems, 3-tank system, interacting system, non-interacting. So that was all my PhD work. Currently, I am with the Institute for Infocom Research from last year. It's ASTAR, Agency for Science, Technology and Research. I am in the division of Intelligent Transportation Solutions. And here I am responsible for the design and implementation of control algorithms for public bus operations and services in Singapore. Before that, I was working as a research fellow for 2 years with Nanyang Technological University, NTU, Singapore. So there I was involved in 2 projects, one with the Smart Mobility Experience Lab and another one with Energy Research Institute, ARIAN Lab at NTU. So the first project was based on the developing the algorithms for V2X protocols and applications. So today's presentation will be focusing on the work which I have carried out as my postdoctoral work at Smart Mobility Lab NTU. And later I was moved to another project on developing algorithms for motion planning, localization, physics-based rendering for various use cases to be tested. And also have 5+ years of teaching experience in the academics in Engg University. So in my outline of the presentation, I'll be giving some introduction to what you mean by platoon, the concepts behind platoon of vehicles, and then an overview of some of the terms which are used in the vehicle-to-vehicle communications for platoon testing. So something like V2X, V2I, so a lot of communication constraints. Then I'll be moving on to the control algorithms. Basically, I'll first tell the difference between the basic control, which is the ACC, which is adaptive cruise control. And later I'll tell what's the difference between ACC and CSST, the advanced version of ACC. Then some combinations of platoon maneuvers, mainly splitting and merging. And I'll project some of the simulation results. So my presentation will be like in a simple way so that everyone can understand. I've not included much depth analysis what we have carried out during my postdoctoral work here. So now coming into the topic, platooning. So when this project was given to me, I was trying to relate this work with my day-to-day life experience. So hope everyone must have done their NCC training at their school times. So, or maybe some march parade or march past during your Independence Day at school. So where we can see one leader will be there in the march past who will be leading the way, and he'll be transferring some sort of information to the follower people, like who is following that leader. So the person behind that leader may be considered as some row 1, row 2, row 3, some n rows will be there with many peoples in it. So whatever the pace the leader is moving, the row 1 cadets also has to move on the same pace. They have to maintain some distance between the front leader as well as the behind row 2. So similarly, the row 2 has to maintain the same pace as row 1, and it has to maintain a distance between the front, back, as well as the left and right. So this is a basic scheme we have observed in the during our March 1st for NCC training. So the same concept is what applied for the platooning of vehicles. So now instead of considering people here, we are considering vehicles. So in March 1st, what we are doing was there is some information being transferred. So person will be sensing, or he'll be doing his perception to understand he'll sense the information such that how many people are there in front, what distance he has to maintain, and he hears some other information through his ears, and then understands what he has to do, and from his brain some control action is happening. Then it comes in the flow of the pace, speed of the movement of the legs, movement of the hands. All these things comes from the brain. So this is the control action. So basically we see some three processes here. First one is the perception, like gathering the information from the surroundings. Then that is he can transfer that to an understanding level, which means the person has to understand what are this information and what to do with this. So he does some processing in his brain, and then it is transferred in the form of control actions. So control actions here will be in the movement of legs and speed of that person for that coordination, whatever is there in that NCC training. So coming to the platoon, the basic definition of a platoon is it refers to a group of vehicles that are moving at a same speed on road, which is in a pattern, or it is connected wirelessly. So the most common pattern is a straight line that we observe with vehicles, then which is moving one behind the other in the same lane. So the first vehicle will be, as in the case of this realization I've said, the first vehicle sets as a pace, which is a speed, and the remaining vehicles has to adjust their speed to match the first vehicles. So the first vehicle is manually driven, or it is like a certified driver will be there. It can be either autonomous or semi-autonomous, which is in between. You can switch from autonomous to manual, manual to autonomous, and the remaining vehicles will be in the form of what I said is a semi-autonomous. So the main advantage of using this vehicle platooning on roads, the concept is like it aims to increase the capacity of roads. That is one advantage. The second advantage is on the improving the traffic safety, and then reduction in the fuel consumption. So a V2V is a concept what is not next I'm going to elaborate to you. Before that, we should know what you mean by V2X. So V2X means vehicles to X means infrastructure. It can be everything. So V2X is a vehicular communication system that has many specific types of communications. So in literature, we can see the V2X stands for everything, but this everything can be either an infrastructure, which is V2I, then it can be a vehicles to network, which is V2N. Then we have vehicles to vehicle, which is V2V. Then we have vehicles to pedestrians or passengers, which is V2P. Then we have vehicles to device, which is V2D. Similarly, we have another concept which is in V2G, which is vehicles to grid. So here, the V2X terminology, what I'm representing is like V2V and vehicles to infrastructure communications, which are collectively termed as the vehicles to in everything communication here. So there are two types of devices which is used in vehicles to everything communication. So the first one is the onboard units, so which is abbreviated as OBUs. And the infrastructure is equipped with the roadside units, which is RSUs. So these RSUs can be placed in traffic lights, whereas OBUs can be placed on the vehicle, either on the bus or on the truck or on the car, any other vehicular objects. So the vehicles are equipped with onboard units, and the infrastructure is equipped with the roadside units. So what it does is OBU transmits the vehicle state information, and the RSU transmits data depending upon the infrastructure at which they are installed. So suppose we take a case where RSU at in intersection transmits a traffic signal data, whereas OBU will be transmitting the information of the speed, everything to the infrastructure so that it can use for the particular use case. So to ensure the quality of service in V2X, the communication, then the wireless standard must support a high frequency and a low latency data exchange. So what we does here is the purpose of V2X is to create some network of communicating vehicles. So that is done. Then the various use cases are used to test the algorithms. So such as optimal speed advisory communication. So which is nothing but GLOSA, we'll say. So that is green light optimized speed advisories. So which means every vehicles will be equipped with OBUs and it will communicate with the traffic light, which is the RSU. And depending upon the vehicle density, all the vehicles will be communicating with the RSUs and it will be transmitting some data. And based on that, the vehicle will be receiving some information such that if they go in a particular speed, then they can cross that signal in green wave. So that is the information word. So it is upon the driver to accept whether the advisories has to be followed. If the advisory is like to speed up the vehicle, speed up the car, then if he is not speeding, then he may end up in red signal. So if he is trying to cross the intersection in multiple greens, then it is known as a green wave. And so that concept is coming under the GLOSA. So we have tested this one in real time also at the NTU test tracks. Then it is also used in cooperative adaptive cruise control strategy, which I will be focusing more in detail here. And this also has some use case in intersection collision avoidance. So this is mainly meant for non-signalized intersection where there is no traffic lights at the intersection. The vehicles will be communicating among themselves, and on a four-way road, you can see that the vehicles without any collision, they passes the intersections. So it's like communicating with vehicles to vehicle. No infrastructure is involved in it. So this type of simulation platform also we have developed. Similarly, we have also used some traffic congestion detection and how to avoid the congestions. Also, we have tested the use cases on platooning of commercial vehicles. Other use cases includes in bus bunging avoidance. So we know that there are many same bus service approaching the bus stop at the same time. So there should be some distance between the same bus service. So it's like bus bunging. So we can have a particular time and distance between the buses so that the bus bunging can be avoided. So this type of also can be realized. So to develop all these use case, we need one simulator. So this V2X to test the V2X protocols and applications. So first approach was to develop a simulator which integrates some softwares in it. Then later we need to test this application onto this and then to the real-time deployments. So as I said, we have developed a V2X simulator, which is an integrated simulator platform. So what problems we were having is some of the use cases like intersection collision avoidance, platooning, we cannot directly test on roads because it's a risk of collision is there, and we should avoid such applications in testing in real life. And field trials are very often expensive. So we need to develop a V2X simulator so that we can test these sorts of applications in it. Then a standalone system is not available. So in research community, we can see several simulators have been proposed to study the V2X applications. But since there is no standalone package to study the V2X application, we have come up with a standalone approach for this, which integrate three main softwares, what I'll explain in the next slides. So a combination of these software tools will be allow us to simulate these V2X applications in a realistic way. So for this V2X simulator requirements, what we want is three components. The first one is a mobility, the second one is a network, and the third one is the application. All the control algorithms will be dealt with the application side. The network side is meant for communication section. Mobility is meant for the movement of vehicles. Maybe it should be a a traffic simulator software where we can see the vehicles moving and based on some control application actions from the other software. So other requirements require is a robust and realistic simulator for information exchange. So we should choose the communication model libraries in a much effective way so that simulation time synchronization is good and the capability of modeling the multiple application is possible. And also these algorithms are going to test in 2025 on Singapore. So Singapore is basically a left-hand driving. So all the other applications simulators which is there present in the simulator is a right-hand driving traffic. So we need to develop a simulator which supports Singapore traffic conditions. So that was another achievement what we have come across from this particular development of V2X simulator. So here we can see the basic integrated simulator design. So as I said, the three components are already listed on the blocks as in the form of blocks: the mobility, the application, and the network. So here we can see that to demonstrate the vehicular communication as realistic as possible, we should choose an NS3, which is a network simulator. Which contains some model libraries for simulating the wave architecture. So the wave means it's a bit going into the communication side, but I'll come back to the control later on. So it's like the wave represents for the wireless access for vehicular environments. So wave is actually a family of standards that allow secure V2X communication in a high-speed transport environment. So that is one of the advantage of using a wave architecture. The platoon and the surrounding traffics are modeled in VSIM. So here you can see the mobility component consists of a VSIM, which is a traffic simulator where we built our road network, the calibrated traffic models, the routing decisions, the routing models, then the behavior model of the vehicles, the traffic signal phase timings, controller settings, everything will be done on the VSIM side. So VSIM is basically a software which is meant for traffic simulations. And MATLAB is the next component which is being used to connect VSIM and NS3. So MATLAB is the software which is used for the application component. So all the data exchange what we takes place with the VSIM and the NS3 is through MATLAB. So that's why I said the MATLAB software is used for the writing the control logic or any sort of other algorithms which we need to develop. So the basic data exchange protocols will come like this. The interface between the MATLAB and VSIM is done with the help of COM interface, which is nothing but a component object module. Then VSIM is running on a Windows while NS3 is running on a virtual machine. And MATLAB is run on Windows and NS3 interface are done using TCP/IP packets API protocols. So this is a basic structure of our integrated simulator design. So on the NS3 section, we can see various communication constraints or the analysis. What we can do is on the propagation models, the packet delivery ratio, whether one packet or information from one vehicle to another vehicle has been sent or it has been failed. So those sorts of ratios we can calculate from that. Then what is a delay in a packet receiving by the other vehicle. So all these things, vehicle to vehicle communication, communication related aspects will come in the network component as in the form of NS3. And VSIM MATLAB is through COM interface where the traffic data from VSIM will be sent to the MATLAB. Any change in behavior or like any control action, then we will be sending it through again through the COM interface from MATLAB to VSIM. So all this traffic data will be sent to the NS3, which is running on Linux platform. And NS3 will be doing some analysis based on whether packet has been received, whether depending upon the antenna strength, everything. And then it is sent back all those information from the NS3 section through sockets APIs, and then network packet delivery ratio will be sent using to the TCP client, which is running on MATLAB software. So now coming to the simulation side of platooning. So this platform is used for one of the, I said there are many use cases like Glossa. There is another one which is Glide, which is green link determining. So instead of in Glossa, what we do is we have a fixed time signal, cycle time for the traffic light. So the vehicle speed is given advisories. Whereas in Glide, it's just the reverse, which means that there is no advisory given to the vehicles or any vehicles, but the depending upon the density of the vehicles, some set of vehicles will be allowed to pass the intersection during a particular green phase. So which means that the green timings will be either elongated or compressed so that you can use the intersection in a much better way. So that is another use case. Bus bunching is another. Then platooning is another. So many use cases are there, but I'll be just focusing on the simulation of platoon for this particular presentation. So what we done here is we modeled a platoon, then we designed a controller for this, which is ACC control, and we have used PID controllers, as well as we are tested with the model predictive control to overcome some of the disadvantage in PID. We went with MPC controller, and mainly what we do here is the speed tracking, then maintaining some desired intervehicular distance and packet delivery ratio will be analyzed. So all vehicle platooning, what I am referring here will be in terms of trucks. So we see in modern car and truck manufacturers like Mercedes-Benz, Volvo, then Tesla, Audi, Toyota. So all these car manufacturers as well as truck manufacturer uses the basic ACC algorithm, and then some manufacturer uses CSST for using their use cases better way. So this slide represents the typical autonomous vehicle control block diagram. So in general, all the vehicles are characterized as autonomous when it is capable of recognizing the environment and moving within it without any human interventions. So that autonomous vehicles, or in short AVs we'll say, will detect their environment by using these technologies like radars, LiDAR, GPS, odometry, and computer visions. So hope you might be knowing all these sensors. Radar means radio detection and ranging. Similarly, LiDAR means it is a light detection and ranging. LiDAR is also known as light radars in some papers, you can see that. So so the main sensor which is used here is a radar. So it is one of the crucial sensor which is you can see in ACC or CSST modes. So what it does is it works on the principle of Doppler effect. So it is an object detection system that utilizes radio waves to determine the range and velocity of objects. So it is primarily used to detect vehicles in front and rear. So it also consists of a transmitter to transmit the radio waves, and then we have a transmitting antenna. We have a receiving antenna, a radio receiver, and a processor to do some actuations or something, and to do some required properties of the object in the field. So mainly it is used to determine the location of speed, velocity of the object in consideration. So that is one of the main advantage of using radars. We have also GPS, which is a global positioning unit module, which is initial measurement unit. We'll be getting the location of the vehicle, either the truck or the car. Then we have some cameras for other vision perspectives. Then we have some ultrasound sensors, which is used for park assist for close proximity distance measurement. So radars are used for a long or short, medium distance measurement, whereas ultrasound sensors also uses a transmitter and receiver, but it is mainly meant for the application of close proximity measurement of the distance. So as I said, we have we have something 3 sections here, which is a sense, understand, and act. So for the march past also we had something like perception. The person will be sensing something, then we will be understanding what is the what we have to do, and we have to give the control action to it. So that is in the form of actuation. So it's also here also we have sense, understand, and act. So the perception, sense is nothing but the perception. Understand is meant by planning what to do in it, and act means the action or the actuation what we have to do. So sensing consists of all the sensors, whatever is installed on the vehicle. So it can be a camera, radar, whatever I said, ultrasound, sound sensors. Then 3D is LiDARs, 2D LiDARs. So all these data will be raw data. So it may contain some environmental noise, some interference will be there, and we need to filter all these noises, and so we need to do some sensor processing in it. So next block comes is a sensor processing, where we filter some of the data to make from noise-free data for the processing. Then these data are used as a sensor fusion in the understand level, and then here comes our V2V or V2I communication. Like this data will be used in our simulator design, so that we can find some object parameters based on the timestamp, dimension, the position, and velocity, then map to the a priori informations based on the sensor fusion data. So from this understanding level, then we need to give the action to the do something like warning signals, or complement, or then control, or do nothing, stop, either stop. So these are some of the actuations. So from a high level controller, we need to convert to a low level controller. So understanding output will be a high level controller. So and the action will be in terms of low level control. So from breaking all these, we need to convert to a low level. So there is a challenge there between a high level and low level controller. So that is one thing. On the right hand side, we can see the basic sensor ranges, whatever we use in adaptive cruise control strategies. So for you can see the various sensors. For the park assist, ultrasound is used there. Then we have the surrounding view range. We have the GNS, which is the global navigation satellite system. Then we have the lane departure warning, lane detection, whether it is moving from one position to other position, other lanes. We have the odometry, which represents the odometry is nothing but getting the distance, and we'll be using those distance for calculating whether of the orientation of the vehicle. So all these sensors will be on the vehicle, and we can also go for the actions like emergency braking, pedestrian detection, collision avoidance. So this is the basic sensors and all the actuations what is happening on an autonomous vehicles. So now I'll be giving the next slide as what you mean by is ACC, and how and what is the difference between an ACC and CSST. So before that, the VSIM uses a psychophysical car following model. So what do you mean by the psychophysical car following model means? It suggests that a driver's behavior would vary depending upon the traffic state, such as whether the driver is in the free flow condition, approaching the vehicle in front, or the vehicle, or the following the vehicles in front, or braking. So these type of behaviors are observed with this car following model. So in VSIM, which is a traffic simulator, we uses Windamin 99 and Windamin 79, which is a car following model libraries which are available in VSIM. So the car following model used to detect the driver behavior parameters, and this behavior of the platoon members are were modified in VSIM, and the acceleration and the deceleration is calculated using the CSST algorithm. So what is an ACC is a system that automatically controls the gap between the vehicles driving at a high speed. It's either by actuating the engine and braking controls. So based on some measurements of the distance to the preceding vehicles, Whereas in cooperative adaptive cruise control strategy, we can see an enhancement of ACC that enables more accurate gap control and operations at smaller gaps by adding communication of vehicle status informations from the preceding vehicles. So it is nothing but adding a vehicle to vehicle communication to a adaptive cruise control strategy, which is ACC. It turns into a CSST system. So if you have a vehicle to vehicle communication for in a multiple way, then it forms an CSST algorithm. So the basic idea behind CSST is not only to have the vehicle's cruise control system to maintain a proper following distance behind another car, but also it allows the cars to cooperate by communicating with each other while in adaptive cruise control mode. So what it results is the cars can follow more closely, accurately, and safely. So that is one of the advantage of CSST. So it can follow more closely in the proximity of error, then accurate and safe. Safety is one of the main advantage. And all this will be happening with braking and accelerating cooperatively and synchronously. So that is one of the advantage of this. So in a ACC system, as I said, the controlled vehicle obtains the speed and position of the immediate neighboring vehicles to calculate its control inputs. So for this, we use radar communication for communication between the platoon members. So due to some inherent time delays in radar communication, it is unreliable in some emergency conditions. So to overcome these strong shortcomings of the ACC strategy, we have proposed an advanced ACC, which is adaptive cruise control, where we uses wireless communication standards such as 5.9 gigahertz, which is gigahertz DSRC, which is dedicated short range communication, or it is like 5G communication, which we used in mobile to exchange the data among the platoon vehicles. So the use of wireless standards allows us for the sharing of a wider range of data, such as the GPS position, the IMU unit, then the control actions like throttle or braking. So the access to this more data, what it does is it helps in implementing some advanced control strategies. So that is one of the advantages. So the use of these wireless standards, which allows a low latency and high frequency data exchange, each vehicle in the platoon receives its position, speed, and acceleration of the leader and the preceding vehicles. Then what it does is in a CSCC, the platoon member then uses this information to compute its acceleration, and it results in better tracking of the platoon as a single unit. So from CSCC, we are moving into the CSCC. Most of the CSCC algorithms you will see in trucks, which is manufactured by Benz or Mercedes-Benz or Volvo, then for various use cases. So now coming on to the CSCC algorithm. So the classical control algorithm, what we have considered here is for a longitudinal control of platoons. We have also lateral control, but for the presentation focus, I just consider only the longitudinal, which is like on a straight line or on a highway or an urban streets. So the basic control objective here is the follower vehicle should track the leader speed. Then there should be a constant gap between the platoon vehicles. So say 3 meters, which we are used in the simulation. And there should be also a time gap between the vehicle when the trucks are accelerating. And the basic terminology what we used here is a constant distance and headway time. So we use both the combination constant distance in the algorithm and headway time also in that. So the basic literature starts from the vehicle dynamics and control by Rajamani, where we have the vehicle dynamics for a N vehicle HGV platoon. So HGV means a heavy goods vehicle. We can also see other names for this, which is HDV, heavy duty vehicles, or truck platoon. So these are the other terms which we come across in literature. So we can see there is header vehicle, there is a leader or a follower vehicle in the iteration, then the remaining are set of other following. So this is a concept for a 3HGV. It can be extended for n number of trucks and how the vehicles are communicating. I'll be explaining in detail in the next slides. So I said the terminology used is a constant distance and headway time, but we need to understand what you mean by look ahead concept, which is the policy which we have used in the platooning. So next we'll come to the look ahead platoon. What do you mean by look ahead platoon? So you can again see the three demonstration of a 3 truck vehicle as well as for a, how that varies with the 4 truck and for n trucks. So in a look ahead platoon, the vehicles are controlled with information from the first vehicle and the vehicle which is immediate ahead of it. So this approach gives a better control of vehicles and reduces the risk of collision by multifolds. So in ACC system, what we've seen is we'll be having information about the front vehicles. Only one vehicle at a time will be communicating, and we'll be getting some actions based on we either follow the vehicle just in front. So in ACC, what we does is we'll be having the communication between the other vehicles also, like in multiple vehicles, and we'll be using those concept here. So ACC does not need to consider the multiple vehicle following, since it is only meant for a single vehicle. So whereas a CSST on the other hand needs to consider the multiple vehicles in its design for look ahead platoon concept. So to use a look ahead platoon framework, it is expected to lead to a large benefits for the platooning concept. So the clearance between the member platoon vehicles is generally implemented in two policy, as I said, which uses a constant distance and a headway time. In constant distance, it's a gap between the platoon members is made as constant. So that is a safe distance for the platoons if any packet drops or failures are happening during the travel. And in constant time gap policy, what it does is the gap is proportional to the speed of the platoon. So we'll be addressing this one in the later slides. So coming onto the figure, the platoon vehicles, depending upon the position of the vehicle, it is addressed in different terms in the literature. So in the first figure A, what we can see is it shows a 3HGV platoon, which is connected with the V2V communication. So as you see, the green vehicle is the header of the platoon. So he will be a certified driver, and it is manually driven. A certified driver will be driving the GV, so that is a must requirement. And the follower vehicles can be either autonomous or it can be manual. So it is a semi-autonomous case. So the destination, speed, and the lane are at the driver's discretion. So irrespective of the length of the platoon, the first HGV is called as the header, and rest of the HGVs are highlighted in yellow colors, which is termed as followers. So what it does is it follows the header and are not allowed to take any decision like joining or leaving the platoon without the permission of the header. So it should communicate with the header if they want to leave from that platoon to go to some different destination. And there you can see on the first figure the green arrows. So the green arrows indicates the information exchange between the headers and all the followers which is required in the ACC strategy. So now coming on to the CSST strategy, which is represented in the second one, which is for a 4HGV platoon. Every follower uses some double feedback to determine the control action. So that is the look ahead platoon concept. So the first feedback is what is obtains from the header, and the second feedback is obtained from the leader. So in the second figure, you see that some blue arrows. So the blue arrow indicates that the additional feedback provided by the leaders to their immediate next followers. So it has to be noted that the leader vehicle only provides the feedback. Hence, it is indicated with the help of a single-headed arrow originating from the header to the follower. Now the data exchange of the arrows are indicated in the control design perspectives, as you see in the first figure. So with this V2V communication, all the vehicle exchange will be taking place with all the other vehicles also. So this is a basic concept for 3 and 4 GV. Similarly, we can extend this one to an n number of platoons. So we have also analyzed like we cannot have an n number of platoons. There are some limitations for the communication aspects. So we cannot have 20 trucks following the header. So there is some range in which we need to restrict the number of platoons. So those sort of analysis were also performed during our testing. Now we'll see the modeling and basic control design. So first I'll come to the modeling. So the mathematical model for the platoon of vehicles is explained on this slide. So the platoon is considered to be analogous to a mass spring damper system. So you might be knowing a mass spring damper equation. So which represents by mx n x double dot plus bx, and which is represented that equation. So here n represents the nth vehicle of the platoon. M represents the mass of that particular vehicle. B represents the damping coefficient. Then X represents the position, and U is the input information, the control action to take place. So to implement the platoon controller with the policy I said, constant distance and headway time, a PID controller was formulated. So which is of the structure U of t equal to kp into U of t plus ki integral term plus kd into differential term. So I hope you might have remember the second session of the FDP sessions where Professor J. Prakash has explained about the different control structures which is used in PID formation. So it can be either in the form of a series, parallel, interacting, non-interacting. It can be in the form of lead lag compensators. It can be in the form of filters. So this is the basic PID I have shown for you. I'm not going into detail because in the design we have so this, what is the drawback for this particular one is it's not physically realizable. So because we have the denominator term greater than the numerator term. So the numerator term is greater than denominator. So here what we does is we'll be adding a filter term to this and the designs is like accordingly different based on those equations. So this is a simple PID equations where Kp, Ki and Kd are the proportional, integral and derivative gains. So PID's main advantage is like it's an error minimization for either it can do for servo regulations, servo or regulatory responses mechanisms. So that is one of the advantage of using the PID controller formulation here. Now I am going to define the spacing errors between the vehicles. So here epsilon or the E represents here is a spacing error. X represents the position. Similarly, V represents for velocity for the vehicles. So the vehicles I'm representing in terms of 3 terms, which is suffix as H, F and L. So H represents for header, F represents for follower and L represents for leader. So the basic difference for the spacing errors is for the follower and leader will be the position of the leader minus the position of the follower. So that is normal error term for in terms of position. So into that I am going to add another safe distance, which is HD. So HDFL represents the headway time between the preceding and the follower vehicles. And I said, so that is a constant distance term. Now I need to add the constant time term, which is the headway time. So which is distance, which is represent terms of variation in speed. So it is like HW, which is a time term. So it's nothing but a speed equal distance by time formula. So we know distance is equal to speed into time. So VF into time is HW. So HW represents here is the headway time. So this can be again written as XL minus XF in terms of difference DXFL minus the remaining terms. So similarly for the follower and header. So it's a look ahead platoon. So we'll be having a double feedback. So the spacing errors are represented like this, and the individual HDFH and HWFL, the headway time and the distance between the header and the followers will be represented in terms of n number of vehicles. So we need to extend this to n minus n vehicles. So we are using the term n minus 1 into HDFL. Similarly, n minus 1 into HWFL for HWFH calculation. So we obtain the spacing error. So now the spacing error has to be put into the PID controller, and then we need to rearrange the terms. Before that, we should know what is the force calculated for the platoon of vehicles, which means attractive force, which needs the force to move the vehicle from one position to another position by accelerating something. So it is represented in terms of mu dot equal to fx minus in terms of sine theta cos theta. So for simplicity, we have considered theta to be in terms of 0, and because we are considering a longitudinal longitudinal control here. So C air in that equation represents the rho into the density into AR into CD, and it's a constant term. Fx is known as the attractive force of the vehicles in the platoon. C suffix D, which I said for the explanation for CAR, is a drag coefficient of the vehicle. Similarly, AF represents the frontal area of the vehicles. Similarly, UW represents the wind velocity. So theta is the angle of inclination, and U represents the vehicle forward velocity. M represents the mass of the vehicle. G represents the acceleration due to gravity, and UW represents the wind velocity, and which is a positive for a headwind and negative for a tailwind. So what is this headwind and tailwind? Tailwind is that wind that blows in the direction of the travel of an object. So it increases the object speed and reduces the time to reach the destination. Whereas a headwind is just the opposite of it, which means the wind is against. So tailwind is it blows in the direction. So headwind means it is against the direction of travel of an object. So that is the basic difference, and we will be considering the drag coefficient value to be around 0.2 to 1.5 for our simulation testing. So using these the previous two equations, like the PID, the error, substituting the error terms into the PID, then applying that one with the force equation, then rearranging some terms, then we'll get the control law. So we understood what is a control law, which is for a PID controller, which is the acceleration of the follower. The follower vehicles at what acceleration it has to move so that it can go in pace with the header vehicle. So all this control law will be in terms of parameters like Kp, Ki, Kd, and it will be in terms of XH, XL, XF positions. It will be in terms of acceleration of the header, follower, and the leader. Similarly, in terms of velocity, the speed of the header, leader, and the followers. And the other terms, in fact. So we can see that the HDFH is a term which is there. Then we can also see HWFH, which is nothing I said in the earlier slide, which is the distance between the header and the follower vehicles. Similarly, HW represents the headway time between the follower header and follower leader. Similarly for the other case also. So this is the overall control law. So this is the law we will be mainly using in the control design, which we put up in the MATLAB as the application unit for all the acceleration of the follower vehicles, extended to a number of vehicles. This is for one vehicle I'm showing, 3 vehicles. So what does the proposed control strategy does is this one is meant for the PID algorithm. Later I'll be, if time permits, I'll be going in through the MPC strategies. So a feasible method of PID control for track platooning is what we have proposed in the methodology. So the main highlights is what listed on the slide. So the controller ensures that the follower vehicles track the speed and it maintains a desired gap between the vehicles. So that is one of the advantage what we are using it. And at every instant, every vehicle's broadcast speed and informations. So each vehicle computes its own control inputs using some information from the header and the preceding vehicles. Then there is an ideal communication scenario means there is no failure of packets, like 100% packets have been sent from follower to header to follower, follower to header, all those things. So there is no failures of packets. That means ideal communication. So we have tested the scenarios for ideal communication as well as for the vehicles to infrastructure, vehicle to communication constraints. So in ideal communication, what we've seen is the follower vehicle will always have the information of the header and its preceding vehicles at every time instant. And with V2X or V2V communication constraint, there will be some packet drops. So as I said, we cannot have a 40 vehicles following the header. There's some communication constraint. So we can observe some packet drops in the farther vehicles in the platoon. So this leads to some undershoots and overshoots in the intervehicular distance. So on to the communication aspects, for every 0.1 second, we are broadcasting the packets. And as I said, we are using the wave architecture for the model of communication. Then the module contains IEEE 802.11p and IEEE 1609 standards as a part of the wave MAC layer protocols. And we are using a model with Nakagami embedding used to model the propagation losses. So these are related to the communication aspects. I'm not going into detail. So this platoon we have seen one vehicle following the other. Now what we are going to see is some platoon maneuvers, which means either it can be a merging scenario of a platoon, or it can be in the term of splitting scenarios of platoons. So every maneuvers mean it can either perform these two operations. So if suppose one vehicle from two, there are two platoons moving on the road, and if one vehicle, the one platoon has to communicate or want to merge with the another platoon, then it has to initiate some commands to the header, then some sequence of protocols we need to address, then finally the accept is given for merging initiations. So we are using a ARI protocol for this implementation of communication here, which is nothing but A stands for appeal, replay, and implementation. So these are the three phases: appeal phase, replay phase, and implementation phase. So a vehicle makes an appeal to the header and provides the information related to its request. So it can be either split or merge, what I said. Yeah. So if there is a communication failure, then the appeal is sent again in the next time instant or in the next iteration. So if the reply is affirmative, like it is like confirmed, then the vehicle is allowed to carry out these maneuvers either to split or merge. Then if rejected by the header, then the vehicle can choose to either repeat the appeal or wait for a certain time depending upon the situation. Maybe it might be in the appeal might be given during the platoon moving an intersection. So header can't give the confirmation before while passing the intersection. So he will be waiting. He has to wait for some time so that all the platoons crosses the intersection and then the process is initiated again. So these protocols for merging and splitting maneuvers is what shown on the figure. So the appeal is either a request is initiated by a follower, then the reply is shown in green, which is like approval. It can either approve or reject from the header. Then finally it is like implement, the request is completed or not. So these platoon maneuvers are realized with the help of the simulator design, what we have shown here. Coming on to the ideal communication simulation results, so we have considered a map. On the left hand side, we can see a map of road network 1, which is Alexandria Road in Singapore, where it is a straight line. So here we can see the platoon members were simulated. We have used this, we have created the road layout in Vizim, and we have written the control law in the application side, and then we'll be checking if it is in communication and without communication constraint, how the performance is differing. Also on the right hand side, you can see the speed and intervehicular distance profile of a 14 vehicle platoon. So the first vehicle is the header, and the remaining are the termed as follower vehicles. So you can see different colors represented for it. So initially I raised the speed from 30 km per hour to 50, then raising accelerating to 70 km per hour, then back to stop, which is 0, then again to 40 km per hour. So similarly, we can see the corresponding distance. So as I said in the simulation, when the vehicles are at stop, there should be a safe distance. So here we can see there's a safe distance of 3 meters during the stop, during the time 300 seconds. And similarly, as the vehicles are accelerating, you can see the constant distance plus the headway time will be the formulation in the formula design. And we can see that the vehicles will be maintaining after a particular time instant. So similarly for the other speeds also. So this is like very smooth. You can see all the vehicles fast settling, and intervehicular gap, there is no disturbance, nothing, because it's an ideal communication. I'm not considering any packet loss in this. So when I'm considering the packet loss, which means the V2V communication constraint, this is for another road, which is UVCE, which is in Singapore. So the map road network is what's shown on the left hand side for road network 2, which is shown in Vicen. So on the right hand side, you can see it's not that much smooth. We can see that it takes some time for the FATA vehicles to settle to that particular speed, as well as the intervehicular distance between the vehicle. It takes some also time. So the FATA vehicle, which is represented in either 12 or 13, the follower, you can see it takes more time, or maybe some packet drops will be there in that particular FATA vehicles. So this is the observation, and a lot of analysis are based on this. I'm just highlighting what is the difference between an ideal and what is meant by a V2V communication constraint when we consider the there is some packet loss in the information exchange during the protocols. So that this is for a single platoon case, the ideal communication and V2V communication, what I consider. Now let's see for the splitting and merging maneuvers. So how the platoon? So here two colors are represented here. Red one is for the platoon 1, and second one is for the platoon 2. So the first is for splitting. So we can see the vehicles are moving in the two platoons, platoon 1, platoon 2, with the same velocity. Then at time stamp around 150, you can see that both the vehicles platoons are splitting one to a different destination. So it is moving at a different velocity, and the other one is other like velocity changing. And the 0 here represented that the vehicles are stopping at these 3 signals. So here on the left hand side on the map, you can see there are some signals, traffic signals, and so the 4 stops represents the signals, and the velocity at that will be 0 in that particular case, with the affiliation to the 3 meter distance. So the next one is for the merging scenario. The same road network of USMC is used, where the 2 platoons are initiated with 2 different speed. Then it is allowed to merge at around 200 timestamp. So here we can see the speed and intervehicular distance of a merging scenario. So the timestamp 200 seconds, you can see the red platoon and the blue platoon merges, and then this is under V2V constraint, so it takes some time to settle. Before that, the it reaches the intersection, and then so that's why you're not able to see that settling of that controller design. So on the bottom figure, you can see the intervehicular distance, which is represented in meters. So it maintains some equal 3 meter distance between vehicles, which we have set as in the control algorithm. So we have realized a merge and a split maneuvers using this under ideal and communication constraints. So this is a simulation video where I'll be demonstrating the platoon maneuvers using splitting and merging with V2V communication. So this is a demonstration for a heavy truck platooning. So moving on a one platoon to another in a highway. So here we can see that all this platoon movement is a single form, on a highway. The yellow color indicates that it is the header, and the blue, there are 14 vehicles and it is moving. Now the third vehicle, fourth vehicle from the platoon wants to split. So it gives a request to the first, and now it forms the 2 platoons, and platoon lane change happens. So blue and black. Now merging is going to happen. So the second platoon, the third vehicle wants to communicate and go and merge with the first platoon. So it initiates the ARI protocol. Then you can see that the the fourth vehicle wants to come out. The third vehicle wants to come out, and it will moves out of the blue platoons and reaches to that particular platoons, and the platoon merge initiation is completed onto this. So this is a platoon merging scenarios. This is demonstrated in the VSIM simulations platforms. So it's time there, 3:34, maybe in a couple of 10 minutes, I will try to wind up the unconstrained MPC. So we have tested the MPC and the PID in our control developments. So what problem was having with PID is like it's an error minimization, but if there is a packet, successive packet drops, then PID cannot handle that concern. So in which MPC has some advantage, which means that it will be predicted over an horizon, and if any successive packet drops are there, then it will be taking it into action, and some predictive action can be taken into consideration for the design of the successive failures of information exchange between the platoons. So here we can see, as in the 3HGV platoon, we can also see here a 3 subsystem which is represented in the form of subsystem here. So the first one is the first vehicle, then J-1 vehicle and Jth vehicle. Then we have a reference to that. Then we have MPC controller, and acceleration to all the subsystems will be calculated as a control action. So given a cost function, a finite horizon, constrained optimal control problem is defined to solve to determine optimal values. So here also the MPC controller, the main objective is to maintain the intervehicular distance and headway time between the vehicles for 2 cases. One is for the unconstrained case, and second one is for the constrained case, optimization problems. So the controller starts adjusting the control signal ahead of the reference changes. So in a constrained optimization problem, the controller allows the flexibility to constrain the process variable. So mainly we are considering here is the acceleration and speed of each vehicle to some user-defined limits. So, and it can, what I said, the advantage of the MPC over PID design is that it can handle consecutive packet drops or packet losses and delays in the communication between the vehicles. So in the design, we can see a kinematic model for the design of MPC. So this is nothing but x equal to u plus half AT square formula. So this kinematic model of the MPC, we are using this particular model for the vehicle dynamics. Then we use the discrete time model, which is x dot equal to x plus bu. Then we define y equal to cx, which is the state equations. Then in terms of sampling time TS and the other parameters, we'll be defining the ABC metrics based on MPC. Is one of the criteria or requirement is it should have a good model. So we have to do analysis on the step response, whether the linear and the non-linear model, whether in the step response it should not show much deviation. It should be closer to the dynamics. So that should be ensured first before the design to take place. And the control action, as I said, is in terms of acceleration, change in acceleration. So it is delta AK and delta AK J-1. So all these equations are used to formulate for the constraint MPC, and the reference is defined again in terms of constant distance and headway time. So here we can see HT1 represented in terms of the constant distance and velocity into time. So that is a headway time. Similarly, HT2 represents in terms of HT plus VK into HT for the J-1 vehicle and Jth vehicle, and similarly extended for n number of vehicles. And this input is obtained by minimizing the cost function, which is J in terms of Y transpose Y plus lambda, which is the tuning parameters, multiplied by the control action into delta UK. So the final, if you substitute all these equations, we can represent the delta UK in terms of this one, which is nothing but the change in acceleration for J-1 and change in acceleration for the Jth vehicle. So this is the control goal for the unconstrained MPC. Now, when we're coming into the constrained MPC, all the equations will be the same. Only difference is that we have some upper limits and lower limits. So basically, for our simulation, we have considered the velocity and the acceleration to be the upper and the lower. So we will be using a cost function again to the standard form for a quadratic programming problem. So we use a quadprog, which is used in MATLAB, command used in MATLAB. So again, we'll be defining the cost function in terms of H matrix, which is Hessian and the control unit delta U. And again, H is represented in terms of this. You can go through the MATLAB help so that you can know how to frame this cost function. So similarly, we'll be finding the ABC matrix and the B matrix for this. And finally, we have tested this one for a US freeway highway 5i. So it's a road layout in US. So with the parameters as listed on the right hand side, we have considered the 14 vehicle platoon with the sampling time of 0.1 seconds. The KPK, KD values are tuned based on the so artificial intelligence methods, either using PSO or genetic algorithms, or from the ZN or Cohen-Kuhn or direct synthesis method. Then the prediction horizon is considered as control horizon is considered to be 10. The Turing parameter is considered to be 0.1. Now going on to the results like MPC versus PID, we can see all the difference, all the same similarity of PID and MPC in terms of speed and intervehicular distance, whereas we are giving a constraint on the acceleration. So we can see on the left hand side is the acceleration profile for a PID. Similar response is what we have shown with the MPC controller with no constraints. And the MPC controller with constraints, we can see it is well within that acceleration limit of +1 and -1 meter per second square. So we are giving some constraint to the variable so that we can limit the acceleration as well as the velocity, and response in the remaining, we can see some kicks or some spikes at the speed change, then that can be minimized with the help of the prediction as well as with the help of MPC control. So onto the concluding slide, we can analyze the feasibility of using these controllers for control an HGV platoon with the help of the simulator design. So we propose an MPC controller for constraint issues, and when a platoon moves very maximum or minimum speed limits, a constraint MPC should be used to ensure that the speed does not violate the constraints, and also it guarantees the safety in case of any communication failures or propagation delay. So we can consider all these aspects into the MPC design. In summary, I can say that the concept of platooning is one of the important research topic with V2X domain due to the benefits it brings to the road transport. And a look ahead platoon, which I explained in the previous slides, is used for MPC and PID controller design. And it's a standalone realistic integrated simulator for V2X protocols and applications. And we have tested platoon on this particular environment. So for platoon maneuvers, we have used an ARI protocols, and these are effective in carrying out platoon maneuvers as realistic as possible. So this analysis helps to determine additional sensors which is required to provide a fail-safe alternative in case of any communication failures. Then further, the controller design will be extended to support a variety of vehicles for heterogeneous platoons. So which means here I've considered only trucks. So maybe it can be a truck communicating with a car communicating with the infrastructure. So when this comes into design, then it's a challenging research area where the mass of the element of the or the object will also has to be considered into the controller design, and then the controller goals and controller law will be extremely changing there. So these are some of the publications which came out of this work. And if anyone is interested in like going through this literature or maybe enhancement of the particular simulator platform, then you can just go through this publication where we have given the integrated simulation environment protocols and application testing, then for a PID controller, for the MPC controller. Similarly, for the communication aspect, if you're interested, then we can go for the analysis of packet drops and channel crowding in vehicle platooning using V2X communication. Similarly, we can also, like, 2 papers are in print for an optimal controller for longitudinal and lateral control for the urban environments and highways, and also for the MPC controller design. So you may contact me with the email address or the phone number and I'm like happy to engage and help you out if you have any queries. So if any participants would like to share or ask any questions related to the work, you can just unmute yourself and you can just go on.
Yes, sir. So Naveen wants to know, is there any research work going on platooning in India?
In India, last month, one person from TCS in Cochin, in the InfoPark campus, has contacted me saying that they have initiated the work on V2X and hope in India it may come. I don't know, because the traffic is much congested and the population is huge, and there are many challenges involved in it, but research have been started in particular domain. Like TCS, I see, even though it is a software company, they are also much interested in doing the research. So they contacted me for some clarifications and algorithm development. So yeah, so there are research going on, but to implement in India, it takes some time. So the system should be proper. That's what I can say now. Whereas in Singapore, it is very easy now because of the system is very nice, and we have less number of roads on cars on road, and the population is also very less here.
So next person wants to know whether this concept of platooning is applied for unmanned surface vehicles.
Unmanned vehicles, like you mean
Yeah.
drones, right?
Yeah.
So vehicles only. I think it's for vehicle only they are wanted to know.
Vehicles only, yeah. So so the same algorithm can be, so this is basically the same algorithm which we are using for coordination of vehicles. So coordination concept, this one can be extended to the coordination. It can be used in UAVs or unmanned vehicles, or it can be applied to drones also. So last year, one student has contacted me to apply the same algorithm to applicable extending to drones. So there will be certain fight and drones, and based on their coordination, they need to design some control algorithms. So there are research going on, and hope it may come soon, like they are in the publication state from India.
Okay. Sir, how this platooning will help to save fuel? Can you put light on that?
As I said, the platoon increases. This is one of the advantage. Like it increases the road capacity, and like it increases the road capacity, like maximizing usage of roads, and then fuel consumption is one of the main other advantage of it. So we can avoid the unwanted acceleration and deceleration of vehicles based on the traffic congestions. So if a platoon is moving, then there is, like, we know that it should follow the header and it should maintain the same speed. So it is like vehicles are accelerating at a constant speed. So there is no deceleration or acceleration happening in between. So if it happens, means like there is concerns related to the fuel consumptions. So likewise, we can improve the efficiency.
So there are no questions posted in the chat box, sir. Now participants, if they want personally to ask some question, they can unmute themselves.
I have just given a simple way, maybe in detail, in depth. If you want some clarification, maybe you can contact through email also me. Like I'll really try to respond as soon as possible.
Over to Sir H. Prasanna, sir.
Yeah, thank you.
Yeah, maybe maybe before closing the slides, I would like to share one of the video which is with our partner university, which is NXP Semiconductors in Netherlands. So this is a video for the vision of Singapore for a smarter mobility. So you can just, this is a short video for 1 minute, and you can just have a look on this.
Sir, Anuj sir,
Yep.
one nice question from the one nice question. If there is a sudden accident to header, then the follower will take charge of the header.
We have not tested those cases, but there is one solution which is there for the NXP semiconductor, saying that if something happens to the header, then the immediate follower will be taking its charge, which means that all the powers of the header will be given to the follower vehicle, either to brake, like sudden brake, and then make the follower vehicle as the header vehicle, and then proceed to the target.
Okay, sir. Okay, thank you.
Yeah. Other than this PID and MPC, there are other control schemes which have been tested by the other researchers in the literature, like linear quadratic optimal control schemes. Then we are also using to estimate the vehicle mass on road, or the slope of using some extended Kalman filter. Then extended Kalman filter with MPC is also there in the literature. Similarly, we can see feed forward control, state feedback controllers, then proportional differential controllers. So a lot of controller techniques have been implemented in literature also. So if anyone is interested, you can just use those controllers for the development of the vehicle dynamics.
Okay, sir.
So I thank Prasanna Kumar for inviting me for this session, and hope everyone will is keeping fine
First
during
of all,
the
I
situation.
thank you for kind enough to allow participants to clear their doubts, giving the email and your phone number.
Yeah.
Thank you, first of all. And from the behalf of the department, I thank you, sir. Apart from that one, Dr. Anuj and one more person in the meeting is there, A.V. Nageshwara. We are the participants of, we are the colleagues of PhD in MIT campus, Madras Institute of Technology. When I requested Dr. Anuj Abram, he said okay, but after that one, the time management was the problem, because I think now Singapore is around 4 o'clock.
Yeah.
Yeah. Now
Yeah,
Singapore
it's
is
4
around 4
o'clock.
o'clock. 4 o'clock. So even though he agreed, Dr. Anuj Abram agreed, and thankful for that one. And for the innovative session, that is the platform management, because I hope India also that is going to come, as already Anush said, because what is the mass population and congestion in the traffic, that should be difficult. But one of the challenging aspect in us in India, because Singapore easily can decide. So the research on this one is very challenging, because complexity will be more. So we can use the more and more algorithm, and also we can design ourselves algorithm. This is the one of the challenging. To design that one, please contact Dr. Anuj Abram. I think they
Sure.
might help in this condition. Yes.
Yeah,
So
sure.
we can bring the okay, at least in the what inside of the city it is so more complex. At least we can do that one for the iOS.
Yep.
Yes, Anuj. Yes,
Yes.
Anuj.
Yeah. Yes.
Yes,
It's possible.
we can do the platform the platform management for the iOS. So anybody who are interested, we can collaboratively do the research on that one. Please welcome all for
Yeah,
this
sure.
research.
Yeah, you can
Sure.
contact me at any time. I'll
Anytime.
respond to your
Okay.
mails. Yep.
Respond to you, because this is one of the challenge, because every day you can see the newspaper accidents in the highways because of the high speed or drunken driver. So many happenings going in the highways. So that we can allow by using this platoon management. So we can take it as a challenge. You can design that one. So
One of the use case, the bus bunching, what I demonstrate, like said, it can be implemented in India. Like I've seen in many bus stops, same bus service is approaching at the same time, so that can be
yeah.
avoided with the help of this algorithm.
Yes. That's why in traffic that will take time, but that bus traffic and other traffic we can allow in the highways. We can avoid the accidents and other things.
Yep.
Yes.
Yes.
Yes. And regarding the presentation of the Dr. Anuj Abram, very nice, and he's very collected also the animated video, and he's taken up in the in depth of the platoon management with the algorithm and other things. Thanks, Anuj Abram, Dr. Anuj Abram, and behalf of the department, thanks once again. Thank you.
Okay. Thank
Nageshwar
you very
Rao,
much.
Nageshwar Rao, are you there? Nageshwar Rao?
Yes, sir.
Yeah,
Hi.
Dr. Anuj Abram want to talk with you.
Hi,
Hello, sir.
Nagesh.
Good afternoon. Hi,
Yeah,
hi, sir. Anuj, sir.
we used to talk every month, I think, through Hangout. He has some clarification. I used to like talk with him. So anyway, nice again talking with you.
Okay, sir. Thank
Hope
you.
you're
Thank
keeping
you. Very
hope you're
nice
keeping
to
fine.
see your lecture. It's very good.
Thank you.
Thank you so much for recollecting. And
Okay.
thank you, Prasanna Kumar, sir.
Yeah,
Thank
yeah.
you so much.
Because Dr. Anuj Abram last year Nageshwara conducted the 2-week workshop sponsored from the ACT.
Mm-hmm.
2 weeks continuous. That is 15 days program.
Okay.
Okay. He can last year.
Last year. Fine.
Yeah. Fine.
Okay.
Okay.
That
Thanks
time,
to all.
Prasanna Kumar, sir is the resource person.
Okay, sir. Dr. Anuj
Thanks to
Abram, sir.
thanks to Prasanna Kumar and all the participants for the listening to my session. And hope you have some further collaborations, whatever domain you're working on with the area of my expertise. Thank you all.
Thank you. Thanks to Nageshwar Rao. Thank you.
Thank you, sir. Anuj, sir, and Prasanna Kumar, sir.
Thank you.
Thank you.
Thank you. And all the participants are requested to rejoin 225 for the next session. Thanks. And before completing the session, please take meditation for the 2 minutes, as Karthik sir said. Inhale and exhale. Concentrate on that one. We'll work in the afternoon session. We'll enjoy that one. Thank you. Maheshan, Professor Maheshan, Professor Shobha.
Yes, yes, sir.
We can end this session.
Yeah.
Huh?
You can.
Okay. Madam, you can end this session.
Okay, sir.
Okay, thank you.